So we're going to start off by talking about matter, and later on we'll talk about interactions between different things with matter and what that means. But first of all, let's talk about what is matter. So matter is really pretty much everything you can think of. If it has mass, has some weight and takes up space, it's matter. So let's talk a little bit more about that and kind of what that means. So I want you to kind of imagine an experiment here. I want to know, what would we have, or what do you think we would have if I had an apple and I chopped it in half? So I have two halves of the apple, but they're still both part of the apple, right? Okay. Well, what if I chop one of those halves in half? Still kind of the same thing, right? It's not the whole apple, obviously. It's only a quarter of an apple, but it's still you can take a bite out of it and it tastes like an apple. Okay, so basically I want to keep continuing this. I'm going to cut that in half, and then I'm going to cut that in half, and cut that in half, and cut that in half. And I want to know, how far could I go? Can I just go on forever, or is there going to be a limit? So that's actually my first question. Can I go on forever chopping it in half, or do you think I'm going to eventually hit a spot where I can't chop it in half anymore? Okay, and so as it turns out, there is a limit. There's a point where we can't really chop it in half anymore, or chop it into pieces anymore. And so my question based off of that is, do you think it ever stops being parts of the apple, and maybe it might make more sense for us to think of it as something else? Okay, so that's kind of what we're talking about, and that's what we're going to be talking about in this video. So what is an apple made out of? It's kind of a hard question to think about. We can dig into it a little bit more, but without really, sort of doing some experiments and stuff, that might be tough to know. So basically, an apple is a bunch of different molecules that are organized and combined in a particular way. And I could probably organize them in a different way and get something that's not quite like an apple. Like a pear is probably pretty similar to an apple. It's got a lot of the same molecules, but they're organized a little bit differently. And there's probably a couple different molecules that are there and some that are missing and that kind of thing. So our next question then is, what is a molecule? So have you ever heard of a molecule, and maybe you have an idea of what a molecule is? So the definition we're going to use for this class, and pretty much any science class, is that a molecule is a particular combination and arrangement of atoms. And so if I look at this acetic acid molecule here, you can see I've got a few different atoms. I've got some white ones and some gray ones and some red ones there, right? So that's just one example of one molecule and three atoms. There's, a little over 100 different types of atoms, and there's probably millions and billions of different types of molecules because we can combine them in so many different ways. So the next question then is, what is an atom? Most people have probably heard of an atom. You probably have some kind of idea of what that is. So go ahead and write that in the next question box here. So the definition that we're going to use for this class is, atoms are the building blocks of the universe. So the way you could think about this is, it's kind of like if I made everything out of Legos. Each little individual Lego piece would be one atom. And I could try to make a computer out of Legos, but they're not really. It's not going to work, right? Won't be able to type on it and use the internet and stuff like that. Because they're all really all those Legos are really just Legos. And whereas for atoms, each different type of atom is different, and they have different properties and stuff like that. And that's a whole big topic. That's what you'll learn about in chemistry class. So we're not quite ready for that yet. This is just to get us kind of started thinking about things. So when we talk about atoms, the other word that we're going to talk about a lot is element. And so when we're talking about atoms and elements, basically what we mean is we cannot break them down into other elements. I can't have one atom and I split it apart and I get two different atoms. That's not how it works. Once we get down to atoms, technically you can break atoms into smaller things, but they're not. It's kind of different category then. So let's talk about some examples of elements, because you've probably heard of some of these. One example would be hydrogen. Another example would be carbon. And another example would be oxygen. So you've probably heard of at least one or two of those, if not all three. And it turns out that these three elements are the three that are in our acetic acid molecule here. So the white ones, like this one here and here and here, those are hydrogen. The gray ones are carbon. And then what would you guess that the red ones are? Yeah, so they're oxygen. Okay, so I can put them in this particular arrangement, and that gives me acetic acid. I could put them in a little bit different arrangement. I could have methane gas and carbon dioxide. I could split it up. So molecules you can split up and make other molecules. Elements, not really. Okay, so here's a joke for you. You can't trust atoms because they make up everything. So that's a terrible joke, right? Like you can't trust them because they make things up. But that's not really what we mean. We mean that everything is made out of atoms. All right, so sorry, that's a terrible joke. I got another joke coming up later, but just hang in there. Okay, so I kind of alluded to this earlier, but we actually can break atoms down into smaller pieces, but they're not atoms anymore. They're kind of a totally different thing. And you might have actually heard of these before too. So each atom is made up of three things. And, we have, like I said, hundreds of different, a little over 100 different types of elements, different types of atoms. And they're all made of different combinations of these three things. And those three things are protons, neutrons, and electrons. And so let's talk a little bit about the difference between these three things. So the main two ways we can tell them apart is their charge and their mass. Mass is kind of the easier one to understand. That's basically how heavy it is. And we can see protons have a mass of 1 atomic mass unit, which is just basically very, 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 very small. Neutrons are the same, also 1 AMU, 1 atomic mass unit, so also very, very small. And then electrons, I have 0 written here. Now, if you wanted to get technical here, the mass of an electron is actually not 0, but it's so much smaller in mass than even protons and neutrons, which are already really, 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 really tiny. Like, you don't understand how small they are. We'll talk about that more in a minute. They are so small, so little mass, and the electron is like so small it's not even worth counting, right? So electrons are tiny, very, very little mass. Okay, so that's basically what we mean with mass. Charge is, it's a little bit harder to understand. The best way you can think about it, and it's actually a pretty good way to think about it, is if you walk across the floor and you've got socks on and you're kind of rubbing your socks on the carpet, and then you go and touch a doorknob and you get electrocuted, that's because of electric charge. So you had some positive charge on you or some negative charge on you, and the doorknob has the opposite, and so the charge jumps across to balance things out. So that's kind of what we're talking about here. And so, like I said, it's kind of weird. We have less experience with charge, less way of thinking about it, but we do experience it, and it is relevant for us. So a proton has a +1 charge, +1 charge. So you can remember that because proton starts with a P, and they're positive, and that also starts with a P. Neutrons, now this is where people get screwed up a lot. They say, oh, well, protons are positive, so neutrons must be negative. And yeah, I get where that comes from. But you got to read a little bit further. It's neutron, and so it's neutral, which means basically 0. Okay, so that's a little tricky thing there. And then last of all, electrons, there's no real trick to remembering that one, but electrons are negative. Okay, so that's electron, electricity. Those have the same root there because they're related to each other. We'll talk about that much later. Okay, so anyways, protons, neutrons, electrons, we know their charges, we know their masses. Now, where do we find them? The proton and neutron we're going to find in the nucleus of the atom, and we'll talk about that in a minute. And then the electrons we find in the orbitals, and we'll talk about that in a minute. Now, let's look at this word nucleus. You've probably heard this word, probably seen it, maybe in another science class even. Like in biology, our cells have a nucleus. So atoms also have a nucleus, but an atom is, remember we said, very, 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 very small. And actually, we're going to talk about that in a second. That's kind of the theme of the day, right? As I'm just introducing things, we'll talk more about a lot of this later on. But the nucleus of the atom is like the thing in the very middle. The nucleus of the cell is kind of like the thing in the very middle. So they kind of mean the same thing, but I just want to make the point that protons and neutrons are so much smaller than cells, which are already really small, right? Okay, so let's push forward here. So here's kind of my little drawing that I made of an atom, and you can see there's a couple different parts. So let's pick it apart here. So protons, that's the red ones here, and we see they have a plus charge. That's why I put the pluses on them. And they're in the nucleus. So that's this little part in the middle, right? Well, what do you think these blue things are? They're also in the nucleus, and we only know of one other thing that can be in the nucleus, and that is the neutrons. Okay, so neutrons are blue, they go in the nucleus. They're not actually blue. I put them blue just to help us tell them apart. These things are much smaller than we would ever be able to see, so they don't really have color. Okay, then there is this big gray circle thing all around. And this is another one of those things that's kind of hard to explain, and it's, I drew a picture here, and so this kind of helps us visualize it, but it's really not what it would look like if we could see things. But this is what we're going to call our electron shell, or our electron orbitals. And basically, if I could zoom in on like one little spot down here, like say right there, if I could zoom in, what I would actually see moving very quickly, just for a second I might see it, is a little electron, okay? So maybe it's right here 1 second, and then later it's over here, and it's kind of flying all around, jumping all over the place in 3D. This is not just a circle, it's more like a sphere or a ball. So it's going to be flying all around, jumping all around all over the place. But at one moment, maybe it's right there, and that's when I see it. And that has a little negative charge, right? So orbital is kind of like, we are orbiting the sun, or the moon orbits the earth. And it just kind of means like going around the outside, right? Now, the moon and the sun are orbiting things, and the earth orbiting things, that's like a very nice, smooth, predictable thing. Electrons are, like I said, they're going crazy. They're flying all over the place. So similar, but not exactly the same. But there might be more than one electron, okay? So I have one electron here, but there might be another one over here. And so maybe that's it for this atom, but some of them could have, 10, 20, 30, 40, 50, 100 electrons or more, okay? So this is just like a very small, simple example. And since those electrons are flying all over the place, this whole shell, this whole electron orbital ends up being negative. And then this, again, this is my drawing. This is trying to help you out. But see how these minus signs are a little bit smaller than the plus sign? But maybe if you added them all up, it would be the same as 2 minus signs to balance out the 2 plus signs. I don't know, just a small little thing to notice there. And we'll talk more about charges and all that stuff in just a few minutes. Okay, so we talked earlier, I've said this kind of over and over again, but this stuff is really, really, really small. And so this slide is going to try to hopefully give you an idea of how big some of this stuff is. So let's start with me, Mr. Schober. I am actually not 2 meters tall. I'm only about 1.7 meters tall. But I'm just going to round that to 2. That's what this little symbol here means, is like roughly 2 meters tall, just to kind of give us an idea. Okay, so next thing I want you to think about is your thumb. So how wide is your thumb? How many, and maybe more importantly, how many thumbs tall do you think you are? So if you were going to, stack up your thumbs from the floor up to the top of your head, how many do you think it would take? Well, everybody's, different height and has different, different number of, different width of thumbs. But in general, the width of your thumb is about 0.02 meters. And so that's about 1/100th of a meter. So, roughly speaking, again, these are all just very, rough numbers here. You're about 100 thumbs tall, right? Or I'm about 100 thumbs tall. And so, I move my decimal over 2 spots. That's like, if I moved it 1, it'd be 10 times smaller. Move it twice is 100 times smaller. Okay, cool. So let's move on. So the width of a hair. Now that is, that's pretty thin, right? And so that's about another 100 times smaller than your thumb. And so again, this is all very rough and, just kind of a, big picture idea, but your thumb is, maybe within the range of a couple hundred hairs across, maybe, right? At least that's ballpark area. It's not 10, it's not a bajillion, right? It's maybe about 100. Okay, so here's where things start getting interesting, because even at the width of a hair that is tiny, that's 0.0002. That's one 10,000th, or 2/10,000th, I guess, because I have a 2 there, of a meter. And so it would take about 10,000 hairs or so, roughly, to be as tall as your average high school science teacher. Okay, so now let's go down even smaller. So the width of a human red blood cell, which is, by the way, one of the smallest cells that we have. And we're actually talking here about the smallest part of that cell, and so that is like, another 100 times smaller than your hair, right? But buckle up because we're not done yet. So then let's talk about a helium atom. That atom we were talking about earlier on the last slide, that was a helium atom, with the 2 protons, 2 neutrons, 2 electrons. And look, that's another, several hundred thousand, that's like 1,000, 10,000 times smaller than your red blood cell, right? So you could fit 10,000 helium atoms across the small part of a red blood cell. And, it would take, several thousand of those to get each level up. So basically, like, we're getting really small here, but we're not even done yet. So a helium atom is about, 0.00000000, however many, I'm probably messed up, but, that many meters is pretty small. Next, the width of a proton. Okay, so now look, we went down by another factor of 10, 100, 1,000, 10,000 times smaller than a helium atom is that proton. So that picture I had on the last slide is not to scale. That electron cloud is huge. It's spread out way, 10,000 times the width of just the helium atom. Okay, but don't let that fool you though, because remember, that's just the cloud. The electron itself is tiny, even smaller than that. So now we've got 0.000000000000, go on and on and on, 2 meters. And I just kind of chose to, it's not these numbers are not exact. This is just kind of giving you an idea. So the point that I'm trying to make here is that this stuff is really small. I probably could have just said that on the slide, right? Like, this is really small. But I wanted to give you an idea of just how small we're talking. Okay, so let's move on. So we have got a couple different numbers that we're going to ask about that we always worry about in chemistry and physical science type stuff. And that is the atomic number, and that just means how many protons. The mass number, which means the number of protons plus the number of neutrons. Because remember, if you think back, which of these particles, protons and neutrons and electrons, which 2 have mass? Yeah, it's protons and neutrons. So if we're going to find the mass number, we're going to add up the 2 that have mass, protons and neutrons. Okay, and then if we think about charge, remember neutrons are neutral, so they don't have a charge. So when we're worried about charge, we're only going to worry about protons and electrons. And if you also remember, protons are positive, pp, protons are positive, and electrons are negative. So since they're negative, we're going to subtract them from the positive ones, from the protons. Okay, so let's look at this this little picture down here. This is my little cartoon of a lithium atom. And remember, this is not to scale. These electrons would be much further, spread out much further and much, much, much smaller than they are in my picture. But just so we can see things and count things. So for my atomic number, I want to know how many protons do I have? So how many protons with the plus sign are in my picture? Yeah, okay, there's 3 of them, right? 1, 2, 3. That was easy. All right, so mass number, I want to know basically the number of protons plus the number of neutrons. Okay, so we already know I have 3 protons, so now I need to add the number of neutrons, and together those will be my mass number. So the mass number for this lithium atom is, 6. I have 3 protons, 3 neutrons, gives me 6 total mass carrying particles here. Okay, so we got atomic number's 3, mass number's 6. Let's talk about charge. I have how many electrons here? We got to figure that out. And there's 3 of them, okay. And then I'm going to subtract that from how many protons I had. So take your number of protons, subtract your number of electrons, and for this example, we get 0. So there's no charge. They balance out, right? So we could say it's a neutral atom. There's 0 charge. It's balanced, something like that, right? Okay, so we walked through that one together. Let's have you try the next one here. So here's another helium atom. I want to know what are the atomic number, the mass number, and the charge for this atom. Okay, good. So hopefully you saw that for the atomic number, I'm just going to do how many protons. I got 1, 2. Mass number, I'm doing protons plus neutrons. Well, I already know I got 2 protons plus 2 more neutrons, makes 4 total. So my mass number is 4. And my charge is just protons minus electrons. So I had 2 protons minus 2 electrons would give me 0. Okay, so that was easy, right? All these are easy. It's, there's a lot of math in this, but it's really easy math, right? Like 2 plus 2. Come on, guys, y'all can do that, right? Okay, cool. Moving on here, we got boron. So this one's getting a little bit bigger, a little bit more complicated, but still the same idea. So just add, count, add, and subtract as you need to. So good, I think we got that. So atomic number, how many protons? 1, 2, 3, 4. Easy peasy lemon squeezy. Neutrons, I got 4 there too. So my mass number would be 8. My charge, I have 4 protons, 4 electrons. 4 minus 4 is 0. All right, pretty easy. So these have all been easy examples. I wanted to get you started. Let's look at a little bit different one. So just to make things easier on all of us, instead of drawing the picture, I've just got a little table down here. So if I have a carbon atom and it has 6 protons, 6 neutrons, and 6 electrons, I need you to tell me the atomic number, the mass number, and the charge. Okay, so again, atomic number, there's 6 protons, so that's the atomic number. Mass number, I do protons plus neutrons, so 6 plus 6 is 12, so this would be mass number 12. And I have 6 electrons also, so when I do protons minus electrons, I get 0. So that's, that's the other pretty easy example. But what about this one? Okay, nitrogen. Okay, good. So 7 protons, so atomic number is 7. Mass number, it's going to be 13. And I'm going to have neutral charge again, right? So 7 and 7 balance out to 0. So that was pretty easy. But I want you to see what changed here. So besides, my charge, I guess my electrons went up to balance things out. But my, the only other thing that changed was my protons. So my protons and electrons both went up. And so that means that it stayed balanced, but the important thing that I want to get at here is that atomic number. So the atomic number, which is the number of protons, that tells you what element it is. If we look back at this example, if I have, no matter what the other stuff is, I don't care how many neutrons, how many electrons you have, if you have 7 protons, it's going to be nitrogen. If you have 6 protons, it's going to be carbon. If you have 4 protons, it's going to be boron. We skipped 5, which is beryllium, but you get the idea, right? Okay, so atomic number, really important. Let's move on. Oxygen. How many protons, or what's the atomic number, mass number, and charge for this oxygen atom? Okay, good. You should hopefully have figured this out by now. It would be 8, 16, and 0, right? Atomic number is 8, mass number is 16, charge is 0. But what about this oxygen atom? So the atomic number is still 8. Our number of protons did not change. Our mass number is still 16. Number of neutrons and protons did not change. But my charge now, if I'm going to take my number of protons is 8 and subtract my number of electrons, which is 10, I'm going to get negative 2. Okay? So you can definitely, your charge, so far up until now, every charge that we've done had been 0, but it doesn't always have to be that way. I just chose easy examples, okay? So charge, we talked about that. That's a big deal, right? Let's dig in a little more. So an atom with a charge is known as an ion, okay? That's just what we call it. If you have something called a cation, that means it's going to have a positive charge. That means it has lost an electron. Remember, electrons are negative, so if you lose a negative, that's like gaining positive points. And a way you can remember that is that cation has a T in it, and a T kind of looks like a plus sign, right? So cation, positive, plus. Hopefully that helps you remember that. For an anion, it's negatively charged. That means it gained an electron. It gained an extra minus point. And so my way for remembering that is anion has an N there in it, and N is also the first letter of negative. So N and anion is for negative. So that's one little trick to help you remember that is the T and the N. My other trick is also my other terrible joke. So cats have paws, so cat ions are positive. And there's a little cat with his little paw, right? So I know it's a dumb joke, but maybe it helps you remember it. Okay, so let's go on. So fluorine. How many protons? What's the atomic number? What's the mass number? And what's the charge? And then I want you to tell me, based on the charge, is that a cation or an anion? Okay, so my atomic number, 9, easy. Mass number, 9 plus 9 is 18, also easy. Electrons, 10, so I do 9 minus 10 would give me -1, which means its charge is -1. And if it's minus or negative charge, that means it's an anion. Cool. All right, what about this fluorine? So still 9 protons, so it's still fluorine, right? It could not still be fluorine if it had a different number of protons. That's always, fluorine is always 9, and 9 is always fluorine. They go, they're kind of stuck together there, right? Okay, so atomic number, 9. Mass number, now we have 10 neutrons. So last time we only had 9 neutrons, now we have 10. But I still just add them together. So the mass number for this one here would be 19. Then let's look at our electrons here. Okay, so we still have 9 protons, still have 10 electrons, so we're still -1 charge, still an anion. Okay, but what I want to talk about real quick is this fact that our neutrons changed. So when you have the same atom, so same element, still fluorine here, right? But it has a different number of protons, different number of neutrons. We have the same number of protons, so it's the same element, but a different number of neutrons. We call that an isotope. Okay, we're not going to worry too much about isotopes. I just want you to know the word and just know that it means they have a different number of neutrons. And isotopes are kind of not that important in some ways, and in other ways they're like really important. But again, that's more of a topic for physics class or maybe in chemistry. Talk about that. That's with like nuclear reactions and things. We don't got to worry about it today though, so let's go on. Actually, we're not going to go on because that's the last slide. That's my third and final joke that I tricked myself there. Okay, so lots of questions here, lots of opportunity for you to get hung up on things, but hopefully everything made sense. And once it makes sense, we'll go on to our next video where we're going to talk about the periodic table.